Hello students, I welcome you in today's session of physics. As you all know, we were discussing a topic refraction of light at spherical surface lenses. Clear? This is the topic we had already covered most of the topics of from this chapter. This is your chapter number 16 of optics. Clear? So what we had covered out till now, we had covered out the coordinate geometry, sign convention for measuring distance and lengths, refraction at concave spherical surface. Fine. After that we had covered the lenses. What is lenses, concave, and the type of lenses. This is the topic we had already covered in our previous lectures. Converging and diverging action of lenses. Then we had covered about the same definition, optical center, focal length, focal plane. Clear? These are the things we had already then one thing more, we had already derived the lens maker formula. Clear, for the lenses. After that we are now going to discuss in our today's class the power of lenses. So we will move to here. You can see here, this is the topic we are going to discuss right now, which is your power of lenses. Fine. So we can consider a lens we made up a number of small angle prism. Clear? You can consider a lens, fine, into a number of small angle prism. Clear? So in a convex lens, the bases of the prism are towards the axis. Clear? While in case of concave lens, they are always away from the axis. In a prism, a ray is deviated towards the base. Therefore, when light ray parallel to the principal axis, it means that when the light rays are coming parallel to the principal axis and fall on a lens, they are bent towards the axis in a convex lens. So you have to remember, when a light ray in convex lens parallel to the principal axis, then it always bends towards the where axis, and away in the case of convex lens, and it move away from the axis when you take the lens which is concave in nature. Fine. So thus the purpose of the lens is to bend the light rays. So what is the purpose of the lenses? To bend the light rays. Clear? The more it bends the light ray, the greater is its power. So as much as the light bent by a lens, as you can say, the lens is powerful, or it determines the power of that lens. So a lens of a smaller focal length bends the light ray more. Now you have to remember this line. A lens whose focal length is smaller bend the light ray more than a lens of larger focal length. Clear? So thus smaller the focal length, greater is its power. You can see the relation given here. The power P of a thin lens is equal to the reciprocal of its focal length. This is the relation between the power and the focal length. You can see here. Clear? So P is equals to 1 upon F, which is in meter. Fine. Now we talk about the as unit of power. So the unit of power is how much? It is considered in diopter. This is the unit of power is in diopter. The power of a lens of focal length 1 meter, you can say that it is 1 diopter, or you can write it like this, 1 D. Fine. The power of a lens changes when it is immersed in a liquid. Now what is the effect over the lens when you or the power when you immerse the lens in a liquid? So we have to talk about what is the effect over lens. So if a lens is immersed in a liquid whose refractive index is less than the refractive index of the material of the lens, such as water, then the focal length of the lens, what happen, increases and its power decreases, because as you can see here, we had already discussed that the power and the focal length are inversely proportional to each other from this formula. Clear? But the nature of the lens remain unchanged. So you can say that the power of the lens changes when you immerse it in the liquid, but its nature means when it is either it is concave or convex, it's always as a behave like a concave and convex, but its power will be changed. If the refractive index of the liquid is equal to the refractive index of the material of the lens, then the power of the lens you can say that will be equals to 0, or focal length is infinite. When the power is 0, so from this relation, if the power is 0, then focal length is how much? Is infinite. A lens immersed in such a liquid become invisible if the refractive index of the liquid is greater than the refractive index of the material of the lens. then the nature of the lens is also changed. In that case, what happen? If a lens immersed in such a liquid become invisible, if the refractive index of the liquid is greater than the refractive index of material of the lens. Fine, you have to this is a very important line, you have to remember this. Then the nature of the lens is also changed. So in what cases the nature of the lens changes? When the refractive index of the liquid is more than the refractive index of the lens. Fine. That is, a convex lens will behave like a concave lens. So in that case, what will happen? The convex lens will behave like a concave lens, and a concave lens will behave like a convex lens. That is why an air bubble in water behave like a concave lens. Fine, I hope it is clear. Now we will come to combined focal length of two thin lenses in contact. What is the focal length of two lenses which are combined together? So you can see here, this thing we are going to discuss right now, this one. So you can see here in the figure number 22, this one. Suppose two thin convex lenses, we took here two thin convex lenses, one is L1 and the other one is L2. Fine, whose focal length is how much? F1 and F2, and are placed in contact in air having a common principal axis. So you can see here, this is the common principal axis for both the lenses. A point object O is placed on the principal axis. This is the object O on the principal axis, which is distance is small u. You can see here, this is small u from the first lens L1, and its image would be formed by the lens L1 alone at I dash. So the image of this O object due to lens L1 form at which place? At I dash. Clear? Which is distance V dash from the lens L1. And what is the distance of image from the lens L1? So you can say that it is V dash. Then from the lens formula, we can write it 1 upon V dash minus 1 upon U is equals to 1 upon F1. Fine. Now if I dash serves as a virtual object for the second lens L2. Now this image of the object O, which is formed due to the lens L1, behaves like an virtual object for the lens L2. Clear? Which form a final image I at a distance is small u from it. Fine. You can see here, sorry, it's V not u. Okay, from it, then we can write the same formula 1 upon V minus 1 upon V dash. Now the distance of the object, it behaved like an object for the virtual object for the lens L2. So we can write in place of V u as a V dash. So finally we get the expression 1 upon V minus 1 upon V dash is equals to 1 upon F2. So this is your equation number first, and this is the equation number 2. If we combine both the equation, what we will get here? 1 upon V minus 1 upon U is equals to 1 upon F1 plus 1 upon F2. Fine. So if we replace these two lenses by a single lens which form the image of an object distance u from it at a distance V, then what will happen? Then the focal length f of this equivalent lens would be given by this formula, which is your lens maker formula. So you can write it like this: 1 upon V minus 1 upon U is equals to 1 upon F. Fine. So from equation third, this is the equation number third, and this one is equation number 4. We can write it 1 upon F if you compare both the equations. So from the equation number third, you can see here 1 upon F1 minus 1 upon F2 is equals to 1 upon V minus 1 upon U. So in place of 1 upon V minus 1 upon U, we can write here 1 upon F1 plus 1 upon F2. Clear? So this is the final expression of the combined focal length of two lenses. I hope it is understand. What happens if one lens is convex and the other is concave? In that case, the distance you can know very well. As I told you in our previous lecture, how will you consider the distance of object and the image for the concave and convex lens when it is taken as positive and when it is taken as negative. So from there we put the values of focal length over here. So suppose the focal length of a convex lens is f1 and that the concave lens is f2. So if small f with the focal length of the equivalent lenses, then you can write the formula 1 upon f is equals to 1 upon f1 plus, now the focal length of this concave taken as negative, so minus f2. So what will you get here? 1 upon f1 minus 1 upon f2, and after solving you will get the final expression f is equals to here f1 f2 upon f2 minus f1. Fine, this is the final expression if you took convex and one lens is convex and other is concave. Fine. Now there are few cases given here. What happen if the focal length of the first lens is greater than the focal length of the second lens? Then in that case f is negative and the combination will behave like a concave lens because the focal length of concave lens is taken as negative. Now take the second here, if f1 is less than f2, then f is positive and the combination behave like a convex lens. What happen if the focal length of both the lenses are equal? If both the focal length are equal, then what you from this formula you can write it f is infinite and the combination behave like a plane plate. Fine. So these are the few points you have to remember, students. Now we will talk about the combined power of two lenses who are placed in contact. So if the power of two thin lenses placed in contact be P1 and P2 respectively, then from the equation 5th, from the above equation you can see here, this is your equation number 5. Clear? In place of from the equation 5th you can write it like this: the power of two lenses which are placed in contact is P is equals to P1 plus P2. So you can say that thus the power of the lenses placed in contact are add up if convex and a concave lens of equal focal length are placed in contact. Then the power of the combined lenses will be 0 because there is a P1 is equals to minus P2. Clear? That's why the focal length of such combination will be infinite and it will behave like a plain glass plate. Clear? Now we talk about the magnification by combination of lenses. So when lenses are used in combination, each lens magnifies the image formed by the preceding lens. Thus the magnification m of the final image is given by the product of the magnification by the multiple individual lenses, that is m equals to m1, m2, m3 and so on. Fine, I hope it is clear. Now we will talk about our next topic, which is combination of lenses and mirrors. What happen if you combine a lens and a mirror? So here you can see that this is the figure number 23, the image of real object, clear, formed by a concave lens is always virtual. In order to locate the position of the virtual image and hence to find the focal length of the concave lens is combined with a concave mirror or with a plane mirror. You can see here. Fine. Similarly, the image of a real object formed by a convex mirror is always virtual. With the help of concave lens, you will get a image. Real object formed by a concave lens is always virtual. So again, to locate the position of this virtual image and hence to find the focal length of the convex mirror, the convex mirror is combination with a convex lens. You can see here this from this figure. Combination of concave lens and concave mirror to calculate the focal length of concave lens. Here you can see that here we took a concave lens and concave mirror to find the focal length of concave lens. So the concave mirror is mounted here, you can see that on an optical bench, and a point pin O is placed with its O is placed with its axis on the mirror 23. The position O is adjusted until it is non-parallax with its own image. I hope you know the parallax. There is a parallax means you can say that there is the two different images and you are not able to identify which one is the correct one. So this is called the parallax, and here you can see the position of O is adjusted until it is not non-parallax with its own image formed by the mirror. The pin is then at the center of the curvature of the mirror. So the position of O is noted. Now the concave lens L is inserted between the mirror and O for the object to remain non-parallax with its image. Clear? So it has to move to a position I. This is the position I, you can see here from the figure. This is the I position. Further away from the mirror, O and I on an optical bench are clearly the virtual object and real position for the lenses L. We measure the distance LO, you can see here, or IO and LI of the optical bench. If U and V be the object distance and the image distance respectively for the lenses, then you can write here U equals to LO and V equals to LI. U and V being both positive. Now inserting the value of u and v with positive signs if the lens formula, then what we will get here, the focal length of the lens will be calculated. Fine. So this is the focal length of concave and a convex lens and a concave mirror. Same thing we will do for the concave lens and a plane mirror. Clear? This you can do the same process for the concave and concave lens and a plane mirror. So I hope it is clear for you till now. So this concave lens L is mounted on an optical bench and an object pin OO dash is placed in front of it. The lens formula virtual II dash on the same side of the object. In order to locate the position of this image, a plane mirror is placed behind the lens with its coated surface toward the lens. And the upper end of the on the principal axis, you can see from the figure number 24 here given. This is the figure number 24, and from this figure you can easily show this one. So now another pin you can see here, PQ, is placed in front of the reflecting surface. This is the pin position PQ in such a position that P dash Q dash is the image formed by this lens coincides with II dash. In this situation, the image II dash and the P dash Q dash will be non-parallax. So the position of the concave lens, the plane mirror pin OO dash, here you can see the position of OO dash, and PQ are read on the optical bench. Then for the given convex lens, we write this distances U equals to LO, V equals to LI. LI is MI minus ML and is also equals to MQ minus ML because MI and MQ both are equal. Fine. So after substituting the value, you will finally get this expression 1 upon V minus 1 upon U equals to 1 upon F. The focal length F of the convex lens may be calculated. And the same thing we will you can also do for the convex mirror with a convex lens to calculate the focal length of a convex mirror. Fine. So this is the last one. So the convex lens L mounted in front of a convex mirror mm dash, you can see here, this is the figure number 25A. You can see from this figure, on an optical bench in such a way that the principal axis of the lens and the mirror coincide. Here you can see the principal axis, mirror and the lens. This is the principal axis and they are both are coinciding. An object pin is placed in front of the lens in such a way that the tip O of the pin lies on the common principal axis. Fine. Here you can see this is object pin. Light ray from O after refraction through the lenses fall on the mirror, and after reflection from the mirror, the ray pass again through the lenses and form a real image I towards O. You can see here a real image I which is forming towards O. This is the real image. Now the object pin is moved back and forth in front of the lenses and adjust in a position in which the lens there is no parallax between the pin and its image. In this position, the ray after passing through the lens fall normal to the mirror and hence retrace their path to form the image I dash. As I told you in the previous chapter, when a light ray is normal on the mirror, then it retraces its own path. Clear? So the image I at the same position of the object O, the position of the mirror mm dash is read on both the optical bench. Fine. This is the figure number 2 for the same lens. Now keeping the object and the pin lenses fixed on the bench, the mirror is removed. Since the rays emerging from the lens were falling normally on the mirror, it means that they were converging towards the center of curvature C of the mirror. Hence after removing the mirror, the ray will meet at C. You can see here the rays are meeting here, where the real image I of O will form by the lens located by adjusting the position of an image pin such that image I and the image pin are mutually non-parallax. The difference between the position of the mirror and the image pin is radius of curvature. You can see here of the mirror. The focal length of the mirror is R by 2. This expression we already proved in our previous lecture. So that's all for the today's class, student. Do study properly. Till that, thank you class. Thank you.